So dear students, welcome to today's lecture. Today we will learn very important theorems, okay? And these theorems are called isomorphism theorems. So let us recall what is an isomorphism of groups. Just to recall. So you have two groups G1 and G2, and you say a map is an isomorphism. One is this map is homomorphism. So what does that mean? That means phi of G1 G2 equal to phi of G1 into phi of G2 is true for all G1 G2 inside capital G1, and phi is bijective. Okay, so these two are this property of an isomorphism, and then we call that phi is an isomorphism. Okay. Now there are probably these theorems are probably one of the most important theorems in group theory. So we'll learn these four first theorems, and one by one we will try to give you proof, or sometimes I will give you hints you may prove as a homework problem. Okay. So first theorem. The first isomorphism theorem. So what is the first isomorphism theorem? So how to define it? So let phi from G, say G1 to G2 be a homomorphism okay. So I am assuming G1 G2 or any group, okay, of groups. So it need not be G1 G2 finite, it can be infinite also, okay. And say I am assuming that this kernel of phi, so let me write down the name, say H, kernel of phi, H is the kernel of phi, okay. And then obviously we know that kernel is a null subgroup, so already prove it, okay. Then what happened? Then this G1 mod kernel, which is nothing but H, is isomorphic to image of phi, okay. Image of phi. So image of phi you can obviously write down by the symbol also, phi of G1. Okay. Some people write down this symbol image phi, some people write down phi of G, right? So whenever you have a homomorphism from these two groups, then if you take that kernel and if you question out by the domain by the kernel, then it will be isomorphic. So this is the meaning of isomorphic. Okay. Okay. So let me write down. So if there is isomorphism, then we will say that G1 is isomorphic to G2. Some people also write down phi here. That means the phi is the isomorphism. Phi is one of the isomorphisms. Okay. This is a symbol of isomorphism. So in this case, we write down that G1 mod H is isomorphic to this image of phi. Okay. Now, so what does that mean? So this means that so first of all, you already know that this function. Okay, yeah, so to prove something is an isomorphism, what you need to prove? You need to prove two properties, right? Now, how do I define a map? So let me, okay, so proof. So so let me define a map psi from this G1 mod H, okay, to the say image or phi of G1, whatever, okay. And how do I define the map? By define psi by psi of this. What is the how these elements of quotient group look like? This will be of the form GH, right? Left quotients. And what will be the image? How the elements of this look like? The element of this will look like phi of G. This is the definition. You define psi of GH equal to phi G. Okay. And now, so if I prove that this is the natural map, right? You take a natural element from the domain and you map it to the natural element to the range. This is a natural map. Now we need to show that this natural map is an homomorphism. So first, how to show this homomorphism thing? Uh, so to show something is homomorphism, you need to check this property. So you have say G1 this and G2H belongs to G1 mod H, two arbitrary elements, two arbitrary elements. Okay, so now you need to check that this psi of G1H dot G2H, what is the image of this thing? But this is what? This is nothing but psi of, by definition of the product of log cosets, it will be nothing but G1 G2 of each, right? But by definition of psi, it's nothing but phi of G1 G2. But again, you know that phi is an homomorphism, right? You check it. Phi is an homomorphism, is given. Now if you use the property of homomorphism, then you'll have this phi of G1 and phi of G2. Clear? But what is phi G1? Phi G1 is nothing but psi of G1H, and phi G2 is nothing but psi of G2H. Okay, so I just proved that psi of these two product is nothing but the product of the individual images, right? So image of the product is nothing but the product of the images. So the first property is satisfied. Okay, now I need to check property number 2, that is bijective map or not. So to prove something is bijective or not, you need to check two things. One is this function is injective or function is surjective or not, right? So so what is your guess? So is it injective map? So let us check it's injective map or not. So let us check. So to check something is injective, what you need to check? You need to check that if, so let say psi G1 of H equal to psi of G2 of H. This is given for some for any G1, for some G1 G2 belongs to G1. Okay, and you need to check that if this is the case, then G1, then actually as a cosets G1 and G2 are same. But this is what, by definition, this means this is psi of G1 equal to phi of G1 equal to phi of G2, right? Clear? Now you know that this is phi of G1 and phi of G2, they are element of G2, they both are element of G2, right? So they have inverse to each other, so they have inverse, so you choose inverse of this and it will become phi of G2 whole inverse, and that will be equal to identity of G2. Okay, clear? But what does that mean? That means that this is phi of G1 G2 inverse. This is property of the homomorphism, which is nothing but the identity of it. Clear? So what does that mean? So this means that this element G1 G2 inverse is the element of the kernel of phi, right? So this implies that G1 G2 inverse, this belongs to the kernel of phi, which is nothing but H, right? And G1 G2 belongs to H. That means that this implies, or that, thus it means that as a cosets G1H and G2H are equal, right? Clear? Because A is equal to B if and only if this uh, G inverse H belongs to this, right? So as a cosets they are equal. Clear? So this is fine. So you can easily prove, or you can easily give the other proof also. So instead of G1 G2 you can write down G1 inverse G2 belongs to H, and that you take phi G1 inverse to other side, it will be phi G1 inverse H, phi G2 inverse H. Okay, so these proofs are same. Okay, yeah. So uh, yes. So or I should write down the other way. That will be, I think, better. So instead of these, if I think I should write down this way. This will be, you will understand better. So let me take this other side. Okay. What I will do, I will take this is inverse, other side, then G1 inverse, and then G1 inverse G2, right? And then now it's clear. Okay. But proof is same proof, similar proof. Okay. So this proves that this size, so this implies size 1 1, right? 1 1 means injective map. Now you need to prove some, this is surjective map. So to prove this is to prove this surjective map. What you need to prove? You need to prove that every element has a pre-image. Okay, so let uh, um, something say X belongs to the uh, codomain. Codomain is where yeah. So uh, this is my map from phi of G1. So let me choose from some phi of G1. So X belongs to phi of G1. Okay. Then there exists some G belongs to, or some G dash belongs to G1, such that what happened? It will be image of that, right? Phi of G dash equal to X. This is by definition, right? Okay. So thus you take this element G dash of H, this element of G1 mod H, and you take the image. So this image will be phi of G dash of X, and this was that size onto map, size onto, right? So size both 1 and onto, and thus psi is a bijection psi is a bijection, and hence uh, psi is a isomorphism. Okay, so it's an isomorphism. So what does it prove? It proves that if you have a homomorphism of groups, then you can go modulo the kernel, and that gives you the quotient group, and this quotient group is always isomorphic to the image of the homomorphism, right? Okay, so this is the proof is simple, and so thus we gone. So here I am already assuming one thing, but that we will already prove. So this phi of G1 is actually a subgroup of G2. That we already proved somewhere, right? Or given a exercise. Image of a homomorphism is again a subgroup of the codomain, right? Okay, so this ends the proof, and you have obviously you can easily give some corollary to this fact. So you can say that this so you have this phi from G1 to G2. Okay, and obviously you can write down that immediately you can say that this phi is 1 1 if and only if um, this kernel phi kernel of phi is trivial. So what does that mean? So this is containing only one element. So I should so generally I will write down this trivial, kernel phi is trivial, and this is obvious. So um, uh, I mean, you just this is homework. It's obvious. You don't need a proof for this. Okay. And number two, that also gives you they have the same kernelity. What does that mean? That means G1 mod kernel of phi. This is the quotient group. The number of elements of this quotient group or number of distinct processes of car phi in G1 is same as the number of elements inside the image. Okay. Number of distinct elements in the image. These are simple because it's isomorphism. So you remember, if it is isomorphism, they have the similar property. Like if the domain group is abelian, then the codomain is abelian. It's cyclic, then it is cyclic. So all the properties are same. That's why it is called. It is isomorphism is so important idea. Okay. Once you have isomorphism, you replicate all the property of one group to another one. Okay. So, so this finish this thing. So let me now talk about the second theorem. So the second isomorphism theorem. Second isomorphism theorem. Okay. So in the second isomorphism theorem, what do you do? So you start with a group G. So you have let G be a group, and you have two subgroups, so H and K. They both are subgroups of G with some condition. With what is the condition? Your H must be a subgroup of normalizer of K in G. This is given to you. Okay. So H is inside this, and with respect to this hypothesis, what happened? Um, then many things happened. Then actually, obviously, see, you remember if H is a subgroup of normalizer of Kg, then you know that Hk will be a subgroup of G, right? This is obvious. This part we already proved, and not only that, uh, you just HK subgroup of G, and also you check that K is sitting right, K is sitting inside H, right? So K is a subgroup of G, subgroup of HK, and not only that, K is subgroup of K is not subgroup of HK. So thus you can talk about these, and you can have many things. You can have another subgroups. So let me write down. Mm, say H intersection K, and this is the H intersection K is again a subgroup, not only subgroup, this is a normal subgroup of H. So see, H intersection K is always a subgroup of H, right? But it is in this case it is actually not subgroup of H. So these all are true actually, and with the help of all those things, the final result, the fourth important result is what? That see, this is normal subgroup, this is normal subgroup. So you can talk about the quotient group. So you have a quotient group HK, mod k, and you have another cosine group here, h mod h intersection k, and this theorem tells you that these two cosine groups are isomorphic. This is the important result. Okay, so these two cosine groups are isomorphic to each other. Clear? So so that this first proof we already done in the previous class. Second proof also simple. I think we or maybe I can give you simple proof. See, but you don't need any proof actually. So k is an also proof. Why? Because see, hk is what? Hk is containing. See, okay, just so one. The proof of one already done. Uh, already done, right? Proof of two it is simple. You see that H is a subgroup of normalizer of K inside G. Similarly, K is also subgroup of normalizer of K by definition, right? Because every element of K can always is K, so it belongs to the normalizer, and hence HK is a subgroup of normalizer of K in G, right? And you see, check that K containing HK, right? K inside this. Now K is normal. You know that K and this is inside in okay. And you know that okay, so K is normal here, right? So what you need to check? You need to check that K is also normal here, and how do you prove K is normal here? So mm, okay, so if you choose any element of HK, that will be element of normalizer, and that normalize K, right? And hence this is obvious, right? For so this is normal. This so this okay. So this is so obvious. I am unable to even write. So why? Because for any x belongs to hk, which is also element of uh, normalizer of k in G, and hence x normalizes k, means every element of k normalized by x, and thus um, so x, and so thus k is now subgroup inside hk, right? You understood? X inverse belongs to K for every X belongs to HK. Done. Okay. So this proof was simple. So now property proof 3, what I said. What was that property? Yeah. So H intersection K is also a non subgroup of H. So H intersection say is subgroup of H. You already know. Now you need to prove that H intersection K is a non subgroup of H. And how to prove this? The proof is also simple. So you need to prove that so let you choose two elements, so maybe uh, yes, so let me choose say, so small h belongs to h, and something say h dash belongs to h intersection k, right? So this is an element. uh, so uh, so what I need to prove? I need to prove that um, H inverse, sorry, H dash H dash H inverse belongs to H intersection K. That I need to prove, right? Now, what is the meaning of these elements? So see, you see that um, this is obviously this is belongs to H. Obviously, that is, I mean, H has also subgroup of H. So H has element of H, is element H. So any such product will be element of H. Now, how to prove that this is an element of uh, B? How to prove that? Now you see that I assume these things. So I assume that H is an element of normalizer of K in G. So what does that mean? That means that um, uh, so so those elements which normalize K. So every element of H normalizes K, right? That is the meaning. Because every element of normalizer of K in G normalizes K. So every element of H normalizes K. Okay. So now HK again, AGIN H dash is an element of K also, right? Because H dash element of H intersection K. So H is an element of K also, and thus H dash H inverse is element of K, right? Because as H is sitting inside that normalizer of K in G, right? So every element of H normalizes element of K. So this element is element of K. This is by definition element of H, and hence H dash inverse is element of H intersection K, right? And this is arbitrary. This is for all H belongs to H, and H dash belongs to H intersection K for all such elements. So H belongs to H, not K. H dash belongs to H intersection K. So thus, what we just proved, we proved that H intersection K is a normal subgroup of H. It's not only subgroup of H; it's a normal subgroup of H, right? So so this is so far so good. Now we need to prove that there exists a um, homomorphism, isomorphism from them, right? So now how to prove these two are isomorphic? So this is important. Number 4, the isomorphism group. So what I will prove? I will prove that there exists a homomorphism from this HK to this such that the kernel is K, and this homomorphism is also onto map, onto homomorphism. And then done. Then image will be the proof, and the kernel is K, and then you can use the first isomorphism theorem. Okay, so now let us give the proof, the fourth part. So we define this map say phi homomorphism from HK to um, so H intersection H not H intersection K. Okay. Now what is that the natural map? How do you think? So the natural map should be what? Natural map should be you choose an element from here which will be of the form H and K, small k, and you send it to H, the cosets of H, these cosets. Okay, clear? So this is the obvious map. The obvious map. Element of this domain are of this form. Element of domain are of this form. So you can do the other also. You can do start from this to this also. No problem. But let me just do it from this step. Now, first of all, you need to check that. Now, these are simple check that phi is homomorphism. Okay, this is simple check, and also phi is onto. Okay, do it as a homework. Okay, you know how to check something is homomorphism or not. Okay, and also ontoness. So ontoness is also obvious because the moment you choose some element from here, um, um, any element from here, some H K intersection H, then all there will be always a pre-image, and pre-image is nothing but H itself, right? H itself is a pre-image of that. So ontology is obvious. So these two are simple proof. Now important thing is that you need to find out what is a kernel. Now this is the important thing. So what is the kernel of phi? This you need to find out. If you find out the kernel of phi, then you are done. Okay. Now let us do it. So kernel of phi is by definition all those elements of HK such that image is identity, right? So all those H and K belongs to HK, right? Such that phi of HK, this is the identity. Identity is what? Identity is nothing but the cosets H intersection K. This is the identity, right? Clear? But what does that mean? That means that all HK belongs to HK. What is the image of this? The image of this is nothing but H of H intersection K, which is nothing but H, right? Now we know that if H intersection this is this, that implies, what is the meaning of this? This means that H belongs to H intersection K. This is a property of cosets, right? So H belongs to H intersection K. Now H is an element of H already I know. Now H belongs to H intersection K means H is an element of K also, right? Clear. So what does that mean? So so then where this HK belongs to? You are collecting all those HK, right? So what this HK belongs to? Yeah, I think one more property I need to. Okay, so I need to prove one more property that I will prove it. And then okay, so yeah, phi kernel contains all those products HK such that K is an element of K already I know, H also element of K. So HK is an element of K. So this product is a subset of K. That is clear, right? Because HK intersects HK is element of HK, right? H intersection K. So this product is an element of K. Clear? So what do you have? So you have the kernel is a subset of K. Now we need to prove the converse also. To prove the kernel is actually K. Now converse part is obvious actually. Conversely, um, conversely what happened? Conversely, I mean, if for any kernel K, for any K, you see that it's also kernel. You choose any small K belongs to K, and you check what is that phi of K. Okay, then you are done, right? Now by definition phi of K, image of K is what? See, you define here. So let us recall again. Phi of HK is of this form, right? So phi of HK of this form means what? So you can write down this is identity into K, and by definition this is 1 into HK. But 1 into HK is nothing but the identity there, right? So what does that mean? The image of K is identity. So that means what? That means K is a small K is an element of kernel of phi, or capital K is a subset of kernel of phi, right? And thus they are same. So this is K equal to kernel of K. Okay. Yeah. So thus this proves that H K mod K is isomorphic to H intersections H intersections. Yeah, I hope everything is complete, right? No, I think one part is not complete yet. I should have first proved that. See, this is the way I define the map. How do I know that this is well defined? This is, we need to prove, right? We need to prove that this map is well defined. How do I prove that? Okay, so we also need to prove, so we need to prove that phi is well defined. How do I prove phi is well defined? So what does that mean? How to prove something is well defined map? So you need to prove that if that two elements are same, their image will be same. So how to prove this thing? So let uh, so hk and h1k1 are same. Okay. So or rather I should say other. Okay. So either you can prove by this or you can prove by contrapositive. Uh, maybe this is okay. So if h1 hk and h1 k1, okay. Okay. So if these two are same, hk equal to h1 k1, same elements, uh, then I need to prove that phi of hk equal to phi of h1 k1, right? But phi of hk is what? H, uh, the cosets of hk inside this, right? Now this means what? This means mm, okay. So this is how do I write? So this implies I can write down as some h1 inverse h is same as k1 k inverse, right? From there I can write down. So you check that these elements is already inside h, but this is also inside k. This is inside h intersection k. Clear? Because h1 inverse h is element of h. This is uh, close to under the product, but this is also of this form, and hence this is element of h intersection k, and this implies that h as it proceeds they are same. This is equal to h1 of h intersection k. But this is what? This is nothing but the image of hk, right? Under phi, this is phi of h1 k1, and then this is the proof. So that means that phi is well defined. That we already proved. So now this completes the proof. Okay. So this phi is well defined. You need to prove actually first. Okay. Clear? Okay. Now let us go to the third theorem. So the third isomorphism theorem, and this tells you what? This tells you that you have a group G and two normal subgroups such that so H is now subgroup of G and K is also now subgroup of G. This is given to you with what? With H is a subgroup of K. This is given to you, and then so you can have uh, two cosets actually. Uh, then you have first thing is that if you cosine out by K over H. So obviously you can first prove that K, H is a normal subgroup of K, and that is obvious because H is normal to G. So if something normal to a bigger group, then it's normal to a smaller group also, right? And this is actually a subgroup, not only subgroup, this is a normal subgroup of G mod H. Okay, K mod H is a subgroup of G mod H, but this is more than that. And finally, the most important thing is that if we quotient out by this G mod H by K mod H, because this is normal, so we can take the quotient group, and this group is isomorphic to in case, sorry, G mod H, not G mod K. This is G mod K. Yes. Okay, so and these proofs are also similar proofs, so you need to check, define a map, you need to check those things. I hope this one part is obvious, so I'm not doing proof one is trivial. So homework problem, do it at homework. Okay, and now for proving two, so I will define a homomorphism from here to here and do this thing, right? And then I will use the first isomorphism theorem. Okay, so okay, so yeah, so this is from with first iso theorem. Similarly here also I will use first. Okay, so for number two, what I do, so let me define the map from G mod H to G mod K. Okay, and what are the natural maps? What is that? So you have an element which is of this form, element will be of the form of GK, right? This is a natural map. The element of here is the left coset of this form, element of here are left coset of this form, right? So again you need to first check this is well defined or not. Now to prove something is well defined, one need to prove. So well definedness. So you start with this G1H equal to G2H and check that phi of G1 is equal to G2H or not, and this implies that G2 inverse G1 belongs to H. Okay. Now G2 inverse G1 belongs to H, and what does that mean? So yeah, so what is given? So is given that H is a non subgroup of H is subgroup of K. So this is subgroup of K, and that means that this implies that G2 inverse G1 belongs to K, and hence as a cosets G1K same as G2K. Done, right? So which is nothing but phi of G1H same as phi of G2H. Okay, so this is well defined. Done. Now again the trivial thing you can check homework. Check that phi is onto homomorphism. This you can check easily. Now again we need to find out the kernel. So now important part is that what is the kernel of phi. So by definition this is of the element of the form GH. Okay, such that this phi of GH is the identity. So identity of G mod K is nothing but K, right? Identity of G mod K. Now this is nothing but you write down all the, okay, so you can write down elements of G mod H. This belongs to G mod H, right? So GH belongs to G mod H. What is this? This is nothing but G of K, which is equal to K, and this means that G belongs to K, right? So all those GH belongs to G mod H, such that G belongs to K. Okay. Now G belongs to K. What does that mean? So that means that these left cosets are actually elements of K mod H. So this is actually tells you that this is nothing but K mod H. K. This is a definition, right? K mod H are containing those left cosets of H which are of the form k times h. Here you see that G is the element of k, so this is k mod h actually. And done. So bingo. So now using the first isomorphism theorem. This theorem. Alright, so we have G mod h and the kernel, which is nothing but the k mod h, which is isomorphic to G mod k. Okay, so this is the proof. And see, when I am not writing something, I am saying that homework, I expect that you will do those homework, okay, at your home. And now this last but not the least, this is called the fourth isomorphism theorem. Isomorphism theorems, or it has a very nice name, correspondence theorem. Correspondence theorem. What I said, it said that, okay, so before writing mathematically, let me write down graphically. So you have two kind of sets. In one sets, so you have a group G, obviously, and you have say subgroup, say, which is not subgroup, say H, and on the one hand you have subgroups of G mod H. On the other hand, you have subgroups of G containing H. Means kind of K of this form, which contains H. Okay, this K, this is collection of all those K which satisfy this property, and each is subgroup of this is of this form, K mod H. Okay, subgroup of G mod H of this form, K mod H, right? And correspondence theorem tells you that there is a one-to-one correspondence between these two sets. What does that mean? There is a this is bijection, bijective map of bijections between these two sets, right? So mathematically, how do I write down? So I should write down. Okay, so let me write down. Let G be a group and H be an also group of G. Then there is a bijective correspondence from the set of subgroups of G containing H to the set of subgroups of G mod H. What does that mean? That means for every subgroup of G mod H of the form K mod H, where K is in between H and K. This is one-to-one correspondence. Okay, and then and what you will prove from for this kind of case? So this kind of case you will prove that for any two subgroups, say for any say H1 and H2 subgroup of G, and such that both contain H, so H contains in H1 also in H2. Okay, and in this case, so number one, this so each one is subgroup of H2. This is final leaf. Okay, so let me write down. So here maybe I can use the symbol k bar. So my k bar is nothing but k mod h. Okay, question group I am writing by this bar. Okay, so this is eternal leaf h1 bar subgroup of h2 bar. What does that mean? That means h1 mod h is a subgroup of h2 mod h. Okay, clear. And then this is eternal leaf condition. And if they are obviously if they are subgroup, so if this h1 is a subgroup of h2, then what happened? Then this nice thing happened. Then this index is same. Okay, then this index of h1 inside h2 is same as index of h1 bar into h2 bar, h1 bar into h2 bar. Okay, and these proofs are simple proofs. So similarly, you can prove that intersections, if you have the intersections, sorry, h1 h2, this intersection is nothing but sorry, you take that image of this is nothing but image of this and image of this. So what does that mean? So this means that h1 intersection h2 mod h is same as. So when I'm saying that up to isomorphism, actually I should say that. So this is h1 mod h intersection h2 mod h. Okay, up to isomorphism. And similarly, if you want to find out something is normal inside G, then it will be normal inside that quotient group is normal inside the quotient group. So how do I write down that? Some things H1 is normal subgroup of G if and only H1 bar. This is normal subgroup in G mod H. So what does that mean? That means H1 mod H. H1 mod H is a normal subgroup of G mod H. This is if and only, both the ways. And these proofs are obvious. You just define the map. Okay, so you define the map, right? So and check the bijective map or not. So you define the bijective map. So you choose any k from here. K is of this form. K contains h. Okay, so phi of k you define as k over h, and you check that this is well defined map and this is 1 1 onto map. The proof are simple, so you need to check that phi is a bijection. Okay, and this actually completes the proof. I assume that you guys will do this homework, and on and our next video discussion you can also discuss if we still have some further doubts. Okay, so I will stop here.